Jai Hind. So this is the second lecture in continuation of the previous lecture about the bipolar junction transistor. It's in the previous lecture, in the first lecture, we have discussed about the BJT construction, its working, and the various configurations, the applications, and also we have discussed about the common base configuration and its input and output characteristics. So let's have a recap that what all we have discussed in the previous lecture. So what is BJT? BJT stands for bipolar junction transistor. Why it is called as bipolar device? Because it in case of BJT, the current conduction takes place by two types of charge carriers, that is the majority charge carriers and the minority charge carriers. So there are the two types of bipolar junction transistors we have discussed, that is the PNP and NPN. So in case of PNP, the majority charge carriers are holes and minority charge carriers are electrons, whereas in case of the NPN, the majority charge carriers are electrons and minority charge carriers are holes. So basically, bipolar junction transistor is a current control device. Why we call it as current control device? Because it's in case of bipolar junction transistor, the output characteristics or the output current does not depend upon the output voltage. Instead, it depends on the input current. Means if we are changing the input current, then accordingly the output current gets changed. So BJT is a device which has low input impedance and high output impedance. So there are the three configurations in case of the bipolar junction transistor. Common, because it is a three-terminal device, it has three terminals: emitter, base and collector. So depending upon that which particular terminal is common in the input as well as in the output side, we have the three configurations: the common base, common emitter and common collector. So common base and common emitter, these two configurations are used for the voltage amplification. They are used as a voltage amplifier, whereas common collector is, it is also termed as the emitter follower. It has voltage gain of unity and it is used as a current amplifier. So this is your current amplifier. So basically, these three are having their own applications. So common base is used for the low frequency, high frequency application, and common emitter is used for the audio amplifier. So low frequency application, we use the common emitter amplifier, and common collector is a current amplifier, which is also it has the characteristics that it has low output impedance and high input impedance. So because of that reason, it is used for the used as an impedance matching device for the multi-stage amplifier. Let us understand this, what we mean by impedance matching device and impedance for the multi-stage amplifier. So suppose we are having some voltage amplifier. This is my voltage amplifier. And here we know, and these are all, let's say, current amplifier, common emitter amplifier. I'm sorry. These are my all common emitter amplifier. And we know that in case of common emitter amplifier, it has low input impedance. Its input impedance is low and its output impedance is high. Why? Because emitter base junction is forward bias and collector base junction is reverse bias. So this is again is having the low input impedance and high output impedance, and so on. So here you can see that if we connect these, this is the multi-stage amplifier. So if I directly connect, so because of the low and high input impedance, there will be the lot of voltage drop will takes place, and which cause the loading effect. So in order to avoid that, we need some device which can do the impedance matching, as well as which do not sacrifice the gain of the amplifier. So what if I connect an amplifier which is common collector amplifier, which is having a voltage gain of unity and which has its input impedance high and output impedance low. So here you can see that there will be the matching between the impedance of the common collector and the common emitter, and the gain, it will transfer the gain from the first stage to the next stage. Similarly, here also you can connect the common collector. So basically it is an amplifier which does the impedance matching between the two subsequent stages of the amplifier, voltage amplifier, without sacrificing its gain. So reduce the loading effect. So this is the advantage of the common collector amplifier, or it is also called as the emitter follower. Why it is called as the emitter follower? Because it has the voltage gain of unity. That means that output follows the input. So now we have in the previous lecture, we have already discussed the common base configuration and its input and output characteristic. So now we'll be discussing the input and output characteristics of common emitter and common collector configuration. So here comes the common emitter configuration. So here we can see that this is the NPN type of the transistor. This is my NPN transistor, and here so emitter to base terminal should be forward bias, and because emitter is N type, so that is why we've connected the negative terminal of the battery to the emitter, and the collector terminal should be reverse bias. So N type of collector terminal should be connected to the positive terminal of the battery. So this is your reverse bias. Now here we can see that the input current is IB, output current is IC, and the voltage between emitter to base is, this is the voltage between the terminal base to emitter, it is VBE, and the voltage between collector to emitter, this is VCE. So here you can see that the input current is IB, input voltage is VBE, output current is VCE, and output voltage is VCE, and output current is IC. And now we have to draw the input and output characteristics of the common emitter amplifier, which is common emitter amplifier is used for the audio frequency signal amplification. So, or we can say the low frequency signal amplification. This is the circuit diagram of the common emitter amplifier. This also the circuit diagram of common emitter amplifier, but in this case we have taken the NPN transistor. So we can see that because emitter is P type, that is why in order to make it forward bias, the positive terminal of the battery has been connected, and the collector terminal should be reverse bias. So it is P type. So in order to reverse bias it, the negative terminal of the battery has been connected. So the need of the biasing is to stabilize the Q point in the proper region of operation for faithful amplification. What does it mean? It means that your the transistor should be operated in the active region only, and proper region of operation means the active region. For the faithful amplification means there should be the exact replica of the input signal should takes place. So this is common emitter configuration. Reason that emitter is common to both input as well as the output side. So here is the characteristic curve, input and output characteristics. So input characteristics should be drawn between the input voltage and input current, which is input current is IB in case of common emitter amplifier, and input voltage is VB, and keeping input voltage constant. So initially keeping VC is equal to 1 volt. As we know that in the input characteristics, if we apply only, if we are not connecting this output battery, or you can say the VCCs has not been connected between the collector to emitter terminal, and only VBB is connected, then this is nothing but equivalent to the similarity you can check with that of the the normal PN junction diode. So here you can see that diode, PN junction diode has been forward biased. So there is the similarity between that two. So because of that, here we can see, because this is the silicon diode and silicon type of transistor. So here we can see that up to the almost up to 6 to 7.7 volt, the current will not be flowing, current is 0, and after that your current is increasing, just like the PN junction diode characteristic, VI characteristics of the PN junction diode. This characteristic curve is exactly similar to that of one. Now, if you are changing the, if we are changing this reverse biasing voltage from 1 volt to the 10 volt, then is there any difference or the change in the characteristic will take place? The answer is no. Why? Because this voltage is responsible only for the leakage current. And what is leakage current? That is your ICO. ICO is the very small amount of the current of the order of picoampere or something, because this current is due to only the minority charge carrier. And this current, because the contribution of this current is very, very less, and that is why the characteristic curve is, there's not much difference in the characteristic curve. But if you'll compare this input characteristic with the common base type of characteristic, so you can recall in case of common base, the characteristic curve was between IE and VBE. So because the value of IE is very, very high in comparison to ICO. So that's why the effect of ICO is negligible in case of the common base. But because here the input current is IB, and the effect of ICO in comparison to ICO on IB will be more in comparison to the effect of ICO in IE. And that is why there is some changes in the curve takes place. But again, this change is very, very, this is quite negligible. Okay, so there is no much effect has been taken place due to the reverse bias voltage in the input characteristics of the common emitter configuration. Now coming to the output characteristics of the common emitter amplifier or common emitter configuration. So in that case, your output voltage is VCE, as we have discussed in the circuit, and output current is IC. And now keeping input current constant. So in keeping input current at some value, let's say 10 microampere initially, and then we change the output voltage and measure the current. Here we can see that although the change in the voltage takes place from 0 to 20 volt, but current is getting almost constant. So what is the reason? The reason is that this is a current control device. Means the output current is independent of the input voltage. The output current is that voltage is contributing only for the leakage current. So output current is basically depending upon on the input current. So whatever input current we are setting, accordingly our output current will get changed. But here this is not a perfect horizontal graph. There is some slope. The reason behind that is we know that your beta is equal to IC over IB. So the whatever the value of IB you are setting, that will be the multiplication of the current gain of the amplifier. So the beta times of IB will be the value of IC that you are going to get in the characteristic curve, and that is the reason we are not getting exactly the flat curve. So these are the, so here we can see that the current is changing according to the input current is changing. Now coming to the equation part, here this is your common emitter configuration. Here what if we are keeping output open? So the current which is flowing in the circuit when your base is open, this ICO is the leakage current, ICEO represents the collector to emitter current keeping your base open. This in general you can write only ICO, but if you are you can say the configuration is specific, common base, common emitter, then we use like ICEO. ICEO stands for current which is flowing from collector to emitter keeping base open. So base is open, that's why base current is equal to 0. We know that the total current is given by IE is equal to IB plus IC, and this IE plus IC will give the net current, and this IC is basically consisting of two components, that is your IC majority and ICO, that is the leakage current. So here you can see that, and also in case of common base configuration, we know that alpha is equal to IC over IE. So IC is nothing but alpha times of IE. So from this equation we can get this IC is equal to alpha IE plus IC BO. So IC BO is usually very small and it can be ignored except in case of the high power transistor and in very high temperature environment. So here if we take here instead of IC, we can write it down that IE is equal to IC plus IB, and IC is equal to alpha times of IC plus IB plus ICPO. Now we know that from this equation we can get this, you know this equation, IC is equal to alpha IB by 1 minus of alpha plus ICBO by 1 minus alpha. In this equation, if you keep base current equal to 0, then because we know that alpha is equal to ratio of IC by IE, and IC is nearly equal to IE, but it is less than IE. So that is why the value of alpha is less than 1, nearly 1, but less than 1. So it is 0.996 is the value. If we'll take the alpha key value, value of alpha as 0.996 or 0.994, then keeping that value in this equation, then we get the value of IC should be equal to 250 times of ICBO. So this is the value where if you open the base or keeping the base current 0, then this value is reflected in the characteristic. So when IB is equal to 0 microampere, the transistor is in cutoff, but there is some minority current still flowing in the circuit due to the reverse biasing of the collector to base terminal. So here beta is what is the, it is the amplification factor which is used in case of the common emitter amplifier, and it is there are the two terms beta DC and beta AC. So beta DC in case of the DC mode, and in AC mode beta AC is defined as in the AC mode, and beta value of the beta typically varies from 50 to 400 500 range, and So it is the ratio of the collector current to the base current. In case of AC mode, there will be the alternating current will takes place. So definitely there will be the change in the collector current to the change in base current, keeping your VCE at some constant value. So here from the graph, we can calculate the value of beta AC and beta DC. That will give a clear indication about the beta DC and beta AC. Here we can see this is the graph, and let us say we have chosen these 2 points, and here the change in the current will take place. So here the IB1 and IB2 are 30 and 20 microampere. Similarly, the corresponding IC1 and IC2 are some value. Here you can see that this value is 3.2 milliampere and this is 2.2 milliampere. So keeping that value here, the change in the collector current to the change in the base current, this will give the value of the beta AC is equal to 100. Now, if we take out the center of these two, that is the Q point. Let's say this is the Q point in order to calculate the beta DC. So this is the Q point, and the corresponding value of the Q point, here the IB is equal to 25 microampere and VCE is equal to 7.5, and the corresponding value of the IC is roughly 2.7 milliampere. So putting that value here, the beta DC comes out to be 108. So what is the conclusion out of this? That beta DC and beta AC are reasonably close, and often they are interchangeable. So with this, I stop this video here only. We'll continue with the common collector configuration in the next video. Thank you.